okay, originally was not linearly separable, okay, but we transformed it into a feature space where it was turned into a separable case. All right, this is what we term as the kernel trick. Okay, this is what we term as a kernel trick. So you have a radially separable case like we have in our data set. Okay, it's something like this to the left, isn't it? Okay, so what we do is that we transform these, okay? We transform these into a feature space, and then it becomes what you have on the right, okay? Instead of having it in a circular form, it is transformed, okay? It is transformed into, we will go through that and then you see how it is done, okay? It is transformed and then you have, it becomes a linearly separable case, and then you can use your normal linear way to sort it out. Okay. Okay, so let's see how we do this now. Any questions about this? Any questions about it? Okay. See how we can sort out the kernel trick. Just a minute. So what the kernel trick seeks to do, okay, is to convert something that is like a circle, okay, into a straight line. So when we are able to do that, once it is a straight line, then we can use our linear separable ways to sort it out. Okay. So for instance, we have x1 and then x2. So we can actually map, um, we can map df3, okay, x1, df3, x1 to a figure we term as x1, okay? And then we map df3 x2, okay, to a figure called, a feature space called S2, okay? Please, are you following me?
Yes, Nana.
Okay. Now, we know that when it comes to a circle, okay, if you have S1, okay, S1 squared S1 squared, where is the squared? S1 squared, okay? It's a normal equation of a boundary, okay? We have S1 squared, okay, plus S2 squared, okay, is equal to the squared radius, okay? In this case, our radius was 0.7, isn't it? Please, do you remember that our radius was 0.7?
Yeah.
The one we use in constructing this, okay? So our original radius is equal to 0.7. Okay. So when we square S1 squared plus S2 squared is equal to the squared radius, 0.49. Then what this becomes is a line. Okay, so we have transformed this to this. We have squared it. We have transformed this to this. We have squared it. Okay, so this, what we have here within the, you see this one. Okay, this one. Okay, it was this, and then the df3 s1, okay, was mapped to big x1. Okay, and then this one was mapped to big s2. Can you see the relationship? Okay.
Yeah.
So if we have this one has been marked to x1, this one has been mapped to s2, okay, then s1 plus s2, okay, that's what we have here. x1 plus x2, okay, is equal to the squared radius. This is a line, okay. Therefore, we convert the radially separable case into
Linear.
into linear. Okay, so let's see how we have that. Okay, so let's do that. So let's create a DF4 data frame. Okay. So we are picking DF3. Let's pipe that. And then let's add extra columns. Okay. Where we say that S1 squared. Okay. S1 squared is equal to S1 squared here. Okay. And then we have S2 squared. Okay. Is equal to S2 within the DF3. Okay. F2 squared. Now, before you do this, please, you need to call in, once you are using mutates, call in the dplyr, okay? Sorry. Okay, so let's run this. Oh, I didn't close the, let's run this. Okay, so let's do our ggplot again. So now, what we are going to do is that our slope is going to be our intercept is going to be 0.49. Okay, that's where it will start from. Okay, so let's do our ggplot. So ggplot, we are taking df4. Now we have mapped s1 to x1, okay, big x1, and then small s2 to big s2. Okay, so that's what we have done here. So let's take df4. We look at the aesthetics. Okay, aesthetics. Our x here is equal to s1 squared. Okay, the one we have, the new ones we have created. Okay, and then our y is equal to x2 squared. Yeah. Let's bring our color. Color is equal to y. Okay, so we do a geom point. Geom point. Let's add another layer. So this has created the geom points. And then we do an AB line. We have our slope is equal to -1, and then our intercept will be 0.49, the squared radius. Okay, so you see how this is. Okay, what we want to do is we want to transform it through a feature space in order to, from here, we want to transform it to get something like this on the right. So what we have on the left is what we have in our data set right now. Okay, we want to transform it, okay, into what we have on the right, and that is the kernel trick. Okay, all right. So, all right. So let's run this. Let's give this E4. Okay. Okay. So let's see. Geom point and slope. Okay. Where did I go wrong? So I have the data, aesthetics.
Another double
Okay, so this should be
geom AB line. No, you
the
put
geom.
the slope in another parenthesis into another
Oh, okay,
parenthesis.
okay, okay. Thank you. Okay, so let's run this.
There's still one
Another one inside.
at the end.
Oh, okay, okay, okay. Oh, yes. So when I did the geom line, it brought the
It brought another
part.
parenthesis.
Okay, thank you.
So
Okay.
Nana, is it pushing the data point?
Yes, so the kernel trick is to transform the circular or the data points that is not linearly separable to make it linearly separable so that you can apply a linear separable kernel or any other application that uses linear, okay, to do their predictions.
Okay.
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 So this is just to show you the trick, but we could have just used SVM to plot this. But we have this kernel trick. We have this kernel trick whereby you can convert something that is not linearly separable into a linearly separable case. Okay. Okay, so let's see what we have here. Let's split before. All right, so you see what we've done. We have converted the The colors that I chose here, these are wicked colors. let me just, okay, let me just add a scale color manual to it. Okay, so let's have our values. We have red, and then we have blue.
The
Let me run it. Okay, so now you see the difference. So we have converted something that is radially separable or something that is not linearly separable into a separable case. Okay, and now we can use this to do our prediction. You see how the trick works? Hello, guys. Any questions about the kernel trick?
Yeah, no, that's why I'm saying it looks like it's pushing the data points, like for lack of a better term, it's like
So you see so you see that the first one was round. And remember
yeah.
that the blue one was also here, but per the transformation that we did, okay, we have converted them and put all the blue on one side and all the black on one. Yes. So that is the kernel trick. Okay. So something that is circular, we map it and then it becomes a straight line. And because it's a straight line, we can also use normal predictions to normal linear separable ways to predict. So it's the same information, okay? But now we have turned something that is non-linear into linear. Okay. Okay. Any questions? Any questions? So in the absence of this, you could also just apply how do you call it? Our support vector machine straight away without converting it here. This is just to show you how the support vector machine works. Okay, so let's see how we can do that. Yes, Francis, were you asking a question? Francis, your hand is raised up.
Oh, okay, sorry. I was talking. I didn't know I was mute. Anyway, my diagram did not come as yours. Mine had the red. Should I say? Let me share my screen so that you see. So when my outline is in a different direction.
Did you do it negative? It should be negative.
Yes.
The AB line should be negative.
Yes, it's negative. So I have my outline just like your outline, but my red and blue are in different directions.
Okay, let's see what you have.
Okay.
Wow, I didn't know time will take us like this.
Can you see my screen?
Yeah. Okay.
So you see let me zoom
What is the problem?
my diagram.
Okay, so So it didn't do it. Okay, go back. Did you have a radially separable case? Go back, no, your plot. Go back. You see where the plot is. Go back to the previous, no, don't zoom it. Go back to the previous plot. The arrow that shows on to the left. Yes, go
Okay.
to the previous plots. Yeah. Yes, you had this. So probably you didn't map it well. You didn't map it well. So, okay. So you created this. Did you use DF? Why didn't you use DF3? Why?
Oh, okay. And that's it. Thank you.
Okay. All right. So let's do this quickly and then we go for break. Then, wow. Oh, what do we do? Wow. The timing.
No, it seems Steph has a question.
Who has a question? Stephanie. Oh, Stephanie, yes, please go ahead. Sorry, I didn't see.
Nana, please, could you go up to where you created the circular boundary? I didn't really get the code well.
Okay, let me get my. The code that I use in creating the circular.
Yes, please.
This one.
Nana, please. The radius square.
Yes.
The radius square. No. In the
Yes. So
when we're factoring the DF2, please, if you could scroll to the right. I can't really see the line of.
oh, okay, here. It's radius square, that's all.
Okay, thank you.
Okay, so let's see how the SVM will handle this. Okay, without doing the kernel trick. Okay. So let's do our second data split. Let's copy the data split that we did earlier on. Yeah. Yes. Let's copy this and then bring it down here. Then let's do some small changes. So here we want to build SVM using the polynomial kernel, okay? So let's call this data split 2, okay? So now we are using DF3. Okay. And then we call train set. Since we are using DF3, let's call this 3. Okay, and then test set 3. No, let's use 2 so that it doesn't confuse us. We are using split 2, so we call this also split 2, and then trained 2, and then trained 2. No. Let's make this 3. So it's 3 everywhere. Okay. This was DF4, isn't it? Okay, let's make it 3. So let's run all of these guys.
Nana,
Yeah.
you are still using DF1 in the train set.
Oh, okay. So this one will be DF3, isn't it? Thank you. So let's run this. Okay. So now let's build our model. Okay. So SVM, okay, our Y tilde, everything, comma. Okay. Then we have our data is equal to train set 3. Train set 3. Our type is equal to C classification. C classification. Our kernel. Now we know that this one is not linearly separable. Okay, so we can use the polynomial kernel, and then the degree. Let's say the degree are 2. We have 2 main items in there. Okay? And then the cost by default is equal to 1, is it? Let's call this SVM4. Run this. Page. Type C classification.
Nana, please, is the SV model, the naming.
Oh, okay. Thank you. All right, so let's visualize the model. First of all, let's see what the model tells us. On 20 support vectors. Okay. Degree of 2, cost of 1. Okay. So let's plot this. Plot SVM4, isn't it? First, plot 4. Data equal to train set 3, isn't it? Train set 3. Okay. Let's see. All right, so we see that SVM has the capability of predicting where the data is not linearly separable. Okay. So it can do both for linear and then non-linear, right? So you see the flexibility of the application. Okay. So we can move on to do our prediction. So predict SVM model for we take our tests. Our test set. So let's call this predict test, right? Test, right? Test set deal set 3. Wow. Give you an accuracy of approximately 98%. So you see the flexibility of SVM. Okay. So if you are faced with a situation where you have a non-linearly separable case, and you can determine that it is it's a circle, okay, then you can use the Kedel trick to convert it into a feature space where it becomes linear. Okay. In the absence of that, so you can use your normal SVM, and then you set the Kedel to polynomial and use it to predict. Any question? Okay. It's now 3:50. Can we take, let's say, a 20-minute break and come?
All right.
Okay.
Yes,
Let's take a 20-minute break and come. So let's come back at 4:10. And we see what we can do.
Okay. Okay.
Nana, please, can you move to the SVM model 4 for me?
Okay.
I didn't get that.
Is it okay?
Yes, thank you.
Please say. Hello, sir. Hello, sir. Yeah.
Chrissy.
Nancy,
Don't
maybe
worry,
you
I'm
can
sure
help.
he'll be back very soon.
But you
What
can help me out.
All right. So as we finish this, you should be able to understand the structure of a neural network and then look at feed forward and then feedback neural networks. Okay. And then we'll look at several activation functions. Okay. Identity function, binary step function, sigmoid, and then the ReLU function. Okay. And then we look at the advantages and disadvantages of artificial neural networks. Okay, just a minute. So use cases of artificial neural network or neural network is pattern recognition. Okay, suitable for pattern recognition such as facial recognition, object detection, fingerprint recognition, and stuff like that. Anomaly detection. Okay, it can easily detect unusual patterns that don't fit general problems, and then can be used for time series prediction and natural language processing. Okay, helps with that. So in some places you see artificial neural network. Okay, so these are models for classification and also for prediction. So basically it works like the brain. Okay, the neural network works like a brain where the neurons are interconnected. Okay, and then they learn from experience. Okay, so it's just like the way a human being thinks. Okay, so let's look at a simple structure of the neural network. Okay, so it first of all it receives information. So that is the input layer. Here it picks up input signals and then passes them to the next layer. Okay, so basically we have the input layer, which receives signals and information from the environment. And then it is passed on to the hidden layer. Okay, so the hidden layer is the layer between the output layer. The output layer is where we get the results. So we have the input layer and then we have the output layer. And in between the input layer and then the output layer are the hidden layers. Okay, you can have several hidden layers. So this is just one hidden layer. You could have 2 hidden layers, 3 hidden layers, depending upon the structure of how you want to build your model. Okay. So it does all kinds of calculations and feature extraction. Okay. And then we have the final result, that is the output layer. Okay. So you can have something like this. You have several input layers. So between the input layer and then the output layer, we have the hidden layers, and all these are interconnected. Okay, they could be interconnected. Okay, in some cases not. Okay, so these are the interconnectedness between the layers. Okay, from the input layer to the output layer. Please, any question about this? Any question about this? About the structure of the neural network? Any question about the structure of the neural network? So just like human beings, we receive signals and then we process it, okay? And then we give our output, okay? In terms of the results, yeah? So it has all this, I will not bore you with the mathematical underpinning, but just for your information, okay? So it has weights, okay? All the input signals are weighted, okay? And then the sum of the weights comes together, okay? Plus a bias, okay? Plus a bias. And then it leads to what we call an activation function, okay? Now, the activation function, there are so many functions. So depending upon what we have here, okay, when all of these come together, where you have the summation, when all of this comes together, okay, depending upon the results, will trigger a particular activation function to work, okay? And then it gives you the output, okay? It gives you the output. And there are several activation functions, okay? Right. So there are two main types of artificial neural networks. We have feed-forward artificial neural network. So, and then the feedback artificial neural network. So the feedback artificial neural network means that when it goes through the input layer, hidden layer, and then the output, whatever the information it gets is fed back into the system. So there is a loop. Have you seen? But for the feed forward, it's just one way, okay? It just goes through the input hidden layer to the output, and that's it, okay? All right, so that's the main difference between the two, all right? So the feed forward travels only in one direction, towards the output layer, whilst the feedback, okay, introduce a loop into the network, okay? So it can cause the network behavior to change over time as the network learns from experience, okay? So it is also called the recurrent neural networks, okay? If you see recurrent neural network, it's a network with a feedback loop within it, okay? So let's look at the activation functions, okay? So I was telling you earlier on that depending upon the information that we have here, okay, it will trigger a particular activation function, okay? Or you could sometimes you could even specify the activation function which you want to use. You remember when we're doing SVM, okay, and we're doing the kernels, because we knew the nature of our data set, we specified it to be polynomial instead of linear. Okay, it's a similar concept here. Okay. Okay. So the activation functions, we have identity functions, binary step functions, sigmoid functions, binary sigmoid function. Does the word sigmoid ring a bell? Or does it ring a bell?
That's not classification. Binary.
Okay. Binary. Okay. What about the sigmoid?
The sigmoid rings a bell.
Okay. Which bell does it ring?
When it takes
Logistic regression.
logistic regression,
The
yes, it takes
the S
and
that we
forces
did.
it into
Okay.
zeros and ones.
Zeros and ones. Wonderful. Okay. Okay. So this should tell you that it's something that's related to logistic regression, isn't it? So this particular function. Okay. Okay. So we have various functions. Okay. So the identity function. Okay. Binary step function. Okay. So this is when he's dealing with true or false kind of situations. Okay. All right. So it classifies it as such. Okay. And then when you have a logistic regression case, okay, it can also help. All right. And then we have the rectified linear unit. Okay. All right. That's also one of the functions. Okay. So let's look at the advantages and disadvantages of neural network. And then when we finish, we take a simple example in R and then see how it works. Okay. So neural networks are more flexible and can be used with both regression and classification problems. Okay. Because it has so many functions, activation functions, it can deal with regression, it can deal with classification. Okay. That's another advantage of neural networks. Neural networks are good for nonlinear data sets with a large number of outputs as images. Okay. And then neural network can work with any number of inputs and layers. Okay. And one of the strengths of neural networks is that it does very well when you have a huge data set. Okay. When you have a huge data set. If you have small data set, it doesn't really do well. So sometimes you could have alternative algorithms like the SVM, decision tree regression, okay, which is simple, fast, and easy to train. Believe you me, the kind of maths that neural networks does under the hood, sometimes you don't want to get yourself so bogged down by it, okay? Unlike other ones like regression, which at least you can follow the maths and know what is going on with neural networks. It can be difficult, okay? So neural networks are much more of a black box, okay? Because it does a lot of calculations under the hood and require more time for development and more computation power, okay? And it requires more data, I told you earlier on, okay? As compared to other machine learning algorithms, neural network requires a lot of data for it to give you a good result. Okay, so if you can do something like logistic regression, you can do it using just logistic regression function. Just do it instead of using neural network. Okay, it might be able to do it, but if the data is not very huge, you are better off using other models to do it. Okay, but where your data is huge, okay, then you might consider neural networks. Okay, so basically that's it about neural network. Let's see how we can apply neural network. You see the practical application of it. Okay, and then you'll be able to handle it wherever you see it. Okay, any question? Any question about neural networks? Okay, or you might have some questions when we come to our. So let's see. Okay, let me just break stuff. Okay, the neural networks. Okay, so we need to install some packages, okay? So let's install neural net, okay? Neural net. Okay, so after you are done with the installation, then of course you call it from the library. Run it. Okay, so neural net, and then are we okay? Have you finished downloading it?
Yes.
Okay. So
Yeah.
we call it from the library. And then let's create some data on our own, okay? And then see how we can use this to predict. So let's create a training data set. So here, we just want to look at some examination scores, okay? And whether somebody was selected or not. So just for 2 exams, English. English score. Okay, let's create a vector for it. LS math score. Have your results been released?
No, please.
Oh. Then we use a number to determine whether a person was selected or not. So let's run this guys here. Let's combine the features into a data frame. Okay. So data.frame. Let's combine English score, math score, and then selected here. Let's make it this status. So let's call this train net. So let's create our data frame for the train data. So we could also create the same thing for our test set, okay? Let's copy this. So use this to create our test data set. So I'll change this to 80, 55, 40. And 80. Let's make this 54. And then the math score for the test data. Yeah, 90, 60, 60, 40, 90, 60. Okay. Then the status is 1, 1, 0, 0, 0. Let's skip it. All right. So let's call this test net. Okay. So we created a data frame for this. Okay. We created another data frame. Okay, that's good. Once we've done that, let's create a factor for both the status outcome, okay, or the status variable. So this is a training set. Okay. So before we do that, let's here create the factor.
No,
Yes.
since you didn't change the variable name for the test, what then it overrides the training test variables?
Oh, I changed it. This one, testnet.
No, I'm talking of the English score, math score, and
English for
status.
math.
No, they are all, so no, it will not override it because this one is linked to this data frame.
Okay.
Okay, they are linked to different data frame called, so this one is called testnet and this one is called, it's just like having the same data set and then we split it. Okay. All right. Okay. So we have features here. Let's, we have the combined features. Let's create a factor for the selected. Okay. Or better still, let's create all the factors at once. All of them, so that's it. We'll train and test. Okay, all right. So for the train, we had train, we used train net, isn't it?
Yes.
So train net, let's add F to it so that we know that that's the factored one. Okay. Okay. Better still, we could do it. The train net, okay, is status variable. Okay. So we keep it as it is, and then we do the factor inside. Okay, so let's factor the train net. Status. Okay. So the labels are 1 and 0. So we are mapping them. So these are the levels, and then we map it to the labels. So if it is 1, that means the person was selected. If it is 0, the person was not selected. Selected. Okay. So this one does the, I'm missing something. So this one does the factoring of the status variable in the train. Let's do that for the test as well. Let's copy the same. So this one, we do the tests, okay? So here we factor status in test sets, okay? This one should have gone down here. For status in test set, okay? All right, so this one, factor the test, everything remains the same, okay? All right. Okay, so now let's fit our neural network model. Okay. Are we all on the same level now, please? Are we all on the same level now?
Yes.
Okay. So let's fit the neural network model. Yes, sir. Okay. So let's fit it. So neural net. So we use a neural net, okay? Neural net function. Okay. So here we're looking at status. Okay. It's being predicted. And then we have the English score. English score. English score. We have the math score. We have the math score. Okay. And then our data is we do is train net. Okay. Our data is train net. Okay. And then we specify, we have an argument for the hidden layers. Okay. So the complexity, you can determine the number of hidden layers, okay, based upon the complexity of your data set. Okay. Let's choose 4. You could choose other numbers and then see the effect that it will have on the overall accuracy of your model. Okay. You can play with that later. And then let's specify the activation function. So the activation function here. Okay. So here, the outcome is, we want to make the outcome, how do you call it? A categorical outcome, okay? So we can specify logistic regression. Use logistic. So it uses the activation function for logistic, okay? And then linear output, is there a linear output? Okay, we can set it at false. Linear dot output. I'll set it at false. Okay. So let's run it. Or let's call this NN, okay? Neural network. So when we call this, giving us a lot of information. So basically, we don't want to bother ourselves with the maths. So let's see how it works. Let's see the plot of this. That's a lot of calculations. Okay. Are you seeing my plot?
It's still the vector machine, support vector machine.
You say it's still
I see the support.
So it comes differently. So check your laptop. Okay. At the base, you will see that a plot has generated. Can you see that? Let me see if I can share mine. Can you see that on your laptop?
So I can see it.
Yes.
But that triangle are connected. Hey, I see this plot today.
Okay. You can see mine now. Okay.
Yes, I know you can see it from the input to the output.
Okay. So you know what I was telling you. So it just tells you that somebody does. So you see, basically, don't worry yourself with the weightings of the relationships. Okay. So it's just behaving like a brain. Okay. But you can see the input layers. Okay. You can see the input layers. You can see the hidden layers. Okay. We specified 4, isn't it? Okay. We specified 4 hidden layers. And then it's giving us, so all this interconnects, all right? And then it is able to predict, okay, whether somebody will be selected or not selected. All right? So basically, that's how the neural network works. And it does very well when you have a very huge data set. It does very well when you have a very huge data set. Okay. So let's check the accuracy of our model.
Sir.
Yes.
I'm still confused with the new plots I'm seeing.
Okay.
First, you said the 4 hidden we set is the blue ones.
No. I didn't say the blue ones. You see the one in the middle.
Yeah, there's 4 zeros in the middle.
Those are the hidden. Those are the hidden.
Oh,
layers.
okay. What of those side by side? The 2 on the both left and right.
So these are the outputs. So we have 2 outputs
Okay.
here. We have selected and they're not selected. Have you seen?
Yeah, yes, sir.
All right.
I still don't understand.
Oh, check the data that we said. The data we had.
So sir, when we continue, I might understand. It's just that.
Okay, but okay. Let me still go over. We have input data for English and maths, is it not? Christiana?
Yes, sir. Yes,
we have
sir.
input data for English and math. And both of these come together for somebody to be selected or not selected. So the selected and not selected are our outcome variables. They are the ones here. Okay,
yes,
it's similar to what we have here. Okay. It's similar to what we have here, isn't it? So we have the output layer and then we have the hidden layer. So the hidden layer is what we have in between the input layer and then the output layer. Okay. So our input layer is the math and English. All right.
Okay.
And then our output layer is the selected and not selected.
Understand.
Okay. It's better now. Okay.
Yes, sir.
Right. So it does all these calculations and all right. So
does it mean that's how our brain works, concerning this?
yes, that's how it works.
All right, so thank you.
Okay. All
Mr.
right.
I'm not seeing the graph.
You're not seeing the graph. Check your check the base of your laptop. It is there. And then click on it. It doesn't show in the plot. Okay. You see, share your screen. Let's see.
Oh, I'm using a phone, so I can't share.
You're using a phone.
Yeah, so I'm using the laptop and also the phone at the same time.
Oh, okay. But normally you could connect your laptop to the class so that if you have a problem, how can you share for us to help you? All right. Okay. So it's been plotted. When you go over it, you see. Okay. All right.
Yeah,
So, all right. You've seen it. Okay. Good. All right. So let's look at the let's look at the confusion matrix, and then we check the we'll check the we'll check the accuracy of the model. But before we do that, let's convert our probabilities into binary classes. Okay. So we have some probabilities. Remember that these probabilities are based on, that is what is based on for it to do the prediction. So if it is more than 0.5, then it will base its prediction on the one that has the highest probability. Okay. So check something. Give me a minute. Let me check something. Okay, Thought or something. I'll be with you in a minute. And what I was trying to do was to use this one to do the prediction, but the function that I'm using is not helping. So I'll have to do some investigation to find out.
Nana,
Yes.
when we install the neural nets and call it,
Yes.
there's a feedback that down there that tells us that this function compute has been maxed.
Uh-huh.
Yeah.
Oh, when you install it here, because I have the old
Yes.
one. I have the old one. I have the
So I
old
think
one.
we need to find
So I'll
a
find out. I have the
substitute.
old one. Thank you very much
Okay.
for the information. I have the old one. Normally, when it's not advisable to be updating your R midstream the semester. So I try as much as possible to finish and then I update everything because it takes time. Okay, so I will sort the compute out and then let me see, because I saw something else. Prediction, which is neural network. Okay, let me see the okay, so let me just find out. Let me find out the arguments that So if it's been masked, then there's nothing we can do for now. I'll find out more about it. But have you seen the how it works for the neural network, the artificial activation function, okay, from the input layer to the hidden layers, and then you specify your activation function, and then gives you the output layer. Any question on that? I'll look into this one, the one that has been mastered, and we can use it to do our prediction. Please, any questions about what we've done today? I wanted to, is it possible to meet you tomorrow evening to discuss the assignment?
Nana, we beg, we beg, we beg.
You will not do assignment. We can do it now, but I'm thinking that it's been a long stretch. So, or you let me know during the week the time that will suit you, because tomorrow is we've left with naive base. It's up to you. Do you want us to do it? If you it will take about 30 minutes to do it.
Oh yes,
And
Nana.
then let's do it. Let's do it.
Please, I'm going the extra mile for you, because we've done about 9 models. Okay, it's all to your advantage.
It's true, Nana, and we appreciate it,
I'm really going the extra mile for you, because
Please, can we
it's highly appreciated.
Okay, so you want us to continue now, or you do it?
Let's
I
continue.
think we should rest and then maybe pick a day within the week.
I
to do the
agree.
assignment
Let's
and
rest.
Rest.
Let's
Okay.
rest.
Today is Sunday.
So we just all is left for us to do.
Nana, please, we'll pick a day within the week.
Okay, all right. So let me know ahead of time. Okay, let me know ahead of time.
Thank you very much.
Can we do it between Monday and Wednesday?
Yeah.
Okay, let's do it between Monday and Wednesday, so that we get it over and done with. So basically, we will discuss the assignment. As for the naive base, it's just a simple thing. It's not difficult at all. So we will just do the naive base for about 15 minutes or so, and then we discuss the assignment. Okay.
Banana, I hope the assignment wouldn't be difficult too.
What do you mean by difficult?
So far, the models you've done, we've not so far today we've not really used any data sets to try our hands on it. We just use random guesses to do it. So
yes,
I don't know your examples to your exams wouldn't be this random data set.
No, but you don't have a point, in the sense that the exams, if you've noticed the trajectory of my questions, if I bring a practical something, I ask you to interpret. Okay, so it doesn't really matter the data set. All that matters is the output of the model. So whether I use a small data set or I use a huge data set, the interpretation, if you are wrong for a small data set, you'll be wrong for a big data set. It doesn't really matter. Okay. So in the exams, you are not really asked to, normally you are given an output of a model, and then you are asked to explain the model, or you are given a code and you are asked to explain the code, or a code, you are asked to adjust the code a bit. So as for the adjustment of the code, it doesn't matter whether you have 1,000 rows or you have 1,000,000 rows. Do you get my argument?
Yeah, I get it. It will follow the same syntax.
All right. Yes, yeah. I see your hand raised.
Yes, no. Please, can you share your power again? I wanted to see your prediction, the compute part, the error you got.
Okay. Yeah.
Nana.
Just a minute, Nancy. Let me answer. So the error was. Let me. So the error was. Let me run it again here. Thank you for something. So it was telling me that there was an error in the use method.
Okay. I run mine. I'm not getting an error.
You ran yours, you're not getting an error.
Yeah.
Okay. Because this wasn't giving me an error earlier on. But are you all getting an error if you use the compute? Probably you should do it and let's see.
No, I did not get an error too.
Because sometimes the issue is that different yesterday, for instance, I was having an issue with the I've forgotten. There was something in dplyr that was clashing with the topic that we did yesterday. I've forgotten. So so sometimes for a random forest. So sometimes you can have or I think it was even decision trees. Sometimes you can have you can have a function in a particular package that clashes with another package. So yesterday, for instance, I had to remove my dplyr and then install it again. Okay. So I'm sure if I remove my neural network and then install it again, I'll be able to do the okay. So if that is the case, just a minute. Then we can actually find out the accuracy of the model. Once yours is working, you can share it with me. And then so that tomorrow when we meet this week, we don't go over this again. So if that is the case, you are having the predict, it's working, yeah?
Yes, sir.
Yeah, it is.
Yes.
Okay. So when you can look at the predict, okay, and then you bring the $sign, it will give you the net results. Not
yes.
Yeah. Okay. So if you name this the probability, that gives you just the probabilities. Okay. So run this. Okay. Now that you have saved it under probability, okay, let's do our predictions. So we can call this predict. Okay. So if our probability is normally 0.5, isn't it? So 0.5, then depending upon where it is going, okay, will be either not selected or selected. Okay, so we are wrapping this in an if-else argument, so it makes much more sense. So that should give you your predictions. Okay. So yeah, is it working?
Yes, it is.
Okay, so let's do our confusion matrix. Let's do our confusion matrix. Let's just use a table for our pred. And then okay, but before that, let's see what our actual should be the actual status column, isn't it? So when we take this train test, isn't it? Train, the test, sorry. The test net, isn't it? It was test net. Did you use test net? Yes. So,
Yes.
so the test net, we go to the status column. Okay. So this is our actual values. This is our actual values. Okay. So we name this actual. And then you run it. Mine will give me an error. So when you run it, now you have actual values and then the predicted values. Okay. So compare the table, the predicted, and then the actual. Okay. Are you getting a confusion matrix?
Um,
How does it look like? Can you share it? Let me see. You are getting an error.
Yes. It's stating that all arguments must have the
Yes.
same.
Yeah, I'm also getting the
You are
same.
also getting an error. Okay.
yeah, me too.
Yeah.
The same thing.
What does it say?
Error in table, prayed actual, all arguments must have the same length.
Okay. All right. Okay, call the library for caret, okay, and then run the table again. Library, and then caret. We installed it yesterday. Yeah.
I still got the same.
You're still getting. Okay. Please run line 53. Let me see something. Okay. There. Yeah. Okay. So run the. Okay. Just a minute. Wait. Oh, if that is the case, then your table should not be pred. Okay. Okay. Let me see. Oh, okay. Can you run the call the probabilities? Let me see. Line 55. Okay. Run the prob alone. And let me see something. Come one space down. Okay. Okay, so this is the probabilities we are getting. Okay, run the just a minute. Run the pred and let me see something. 61. Mm-hmm. Oh. Okay.
I don't know.
I see what is happening here. It's supposed to give us one prediction. Okay. And we are having two predictions.
Yeah.
Oh,
So
okay,
now,
okay. So this go to the point where we fitted the model. Go to the point where we fitted the neural model. NN. Okay, run it again. Let me see something. Okay, and then plot the NN. Plot the NN. Yeah. Let's see. Okay. You know what? The okay, I get it now. The data frame. Okay. Where the data frame, where we created the data frame. Okay. Where we created, okay. Just replace the status with selected. So the status, make it selected. Okay, and then change here to selected. Let me see that. So run it again. You need to run it again. So do that.
Yeah, no. For the train, both for the train and the test.
Yes.
Okay.
And then run it again. So everything has to be selected, and then change the factor to.
So everything has been replaced.
So go and run. So here to. Okay, so let's see the plot.
Okay.
Okay, so yeah, let's see that. I'm not seeing. Share the other plot.
Yeah, I'm sharing right now. Please, can you see now?
Yeah. So it has the status. Okay.
Yes.
Okay. So go on again and then run the prediction.
Okay. Okay, now it's getting one.
Yeah.
Okay. Okay. So that's one. Just okay. So now the confusion matrix.
Okay. Good.
Okay.
So you can do the check the accuracy mean into bracket the prediction double equal sign and the actual mean.
Oh, sorry.
Oh, you've forgotten the confusion matrix. So do a comment there so that you remember that is the confusion matrix. The accuracy, sorry. Okay, about 67%. Okay. So please share this with your colleagues. Okay.
Okay, sir.
So I will have to reinstall my neural network. Okay. Yeah, any question? Thank you very much. Okay. Okay, so
thank you, sir.
Okay.
Yeah,
Thank
go
you,
up
sir.
and start.
Yeah, please, you know what to do. Thank you.
I'll share it in the group.
Yes, please share it in the group, okay? And I'll be here for the next 5 minutes, if anything. But please, let me know beforehand, okay? Give me enough time to know when we'll be having the class. But I shouldn't go beyond Wednesday, okay? Let's cut the head of the snake quickly, okay? Oh, but it's been fun. It's been fun having all of you. I've really enjoyed. The time has been short though, but I hope that you've learned something. Okay.
Nana, you're talking like this is the end of like.
Oh, we are meeting again. So yeah. So
Right.
when we meet this week, we are doing the naive base and then the assignment, and that's it. We are done.
And that's it.
Okay.
So
Yes. How many models are we doing now?
We have done about 9. If we
so
do
how many are left? Only one.
9 models.
No.
Yes,
we are left with 1 naive base. You remember?
Making it 10.
You remember the base rule we did when we're doing mathematical foundations?
Yeah.
Yes. So we now have to apply it.
Okay.
All right. So when you were doing the base rule, you thought you were learning something abstract. But it has its application. Okay. Yes.
Listen.
Yeah, please go ahead.
From the slides, I thought we would do a lot under the neural networks, but it's like we just did only this one. Or
so all we have to do is to apply it to various data sets. That's all.
So this is what the neural network. This is all about it, right?
Yes. So yes. So in some cases, you if it is regression, then you have to change the activation function to linear. Okay. I mean, if you are taking the neural network, we could do it for the whole semester. Okay. But this is to arm you so that you can build upon it going forward. All right.
So we only have to change the activation side.
Yes, you change that based upon the data set that you have.
That you have.
Okay.
And last question. Assuming we have a large data, which is best for neural network.
Mm-hmm.
I thought we would do an example of that. And that's of the support vector.
Christiana, even meeting this week, some people are saying that they are tired. Please.
At the end of the day, when you give us assignment concerning
we beg.
Yes, so please, we need to cover. We can't do everything. So I've given you the essential skills that you need.
So can I suggest something?
So the rest is just a minute. So the rest is left with you to do practice. Please, it's about practice. As for data science, it's about practice. If you don't practice, the contrast that you'll be having or the projects that you'll be doing, you go and you cannot do anything. You have to practice, practice, practice. You might even learn some things that we didn't even cover, all right? Because new things are coming in every day, all right? But this is to arm you. If you are doing neural network, at least you understand the mechanics of it. You can handle any problem that comes, okay?
So last one question more.
Yes.
The hidden and the activation, is it the same as the support we're having in the support vector?
No. Why are you linking it with the support?
No, it's like, since we can change the hidden to 4, 5, or any figure.
Yes, so the essence of you determining the hidden depends upon the complexity of your data set.
That's it, okay.
Okay, so if you are just looking at, let's say, relationships between two variables, you can set the hidden to 2.
Okay.
All right. So the more complex your data set is, okay.
The more hidden
yeah, exactly. So you see that the more interactions there will be in between the input layer and then the output layer. All right.
Okay, thank you. So can I beg you for one more time?
So the hidden is actually similar to the degrees when we're doing support vector machines. Okay.
Okay.
Hello,
So
Nana.
can I beg you for one last
Christiana,
Christiana, we beg.
Nana, please,
okay, please go ahead.
please, I want to ask a question on KNN.
Yes, okay.
Are there other ways to calculate for the distance apart from using the Euclidean distance?
KNN normally uses numerical values. So that's why it uses Euclidean distance.
Okay, so that's the
that's what it uses. Yes. Okay. It doesn't use any other distances. So that's why we had to convert all the categorical variables into dummies, zeros and ones. You remember?
Yeah.
Because KNN normally deals with numerical value.
Okay. Thank you.
You're welcome. Okay. Please, any other question? Christian, I think you were suggesting something.
I was suggesting something.
Yes, go ahead. Go ahead. Please go ahead. Go ahead. I'm here because of you.
Because for the support vector and that of the neural network, can you use one of the data sets to just cite an example and send it to the code for us?
So why don't you try it, and then when you are stuck, you get in touch with me, and then I help. In that way, you learn.
Okay, I'll do that. Thank you.